a book, which is kind of nice. I have to ask him about that. So the one-dimensional version of the mean value theorem says that if U is C2 and it's a harmonic function, which is redundant because harmonic functions are C2, in an open set, and if you have, in this case, it's not a sphere, it's a ball, you can think of in one-dimensional ball being the interval, length of the interval, so then U attains its mean value. Now the area, the surface area of the ball is right there, right? So it's the 1D version of the mean value theorem. But here I need a version with inequalities because I want to prove a maximum principle for you that's not equality, that's inequality. So it's not a mean value theorem, it's a mean value inequality. So I was able to just erase wherever there's equality and put an inequality for you. So that's the version that we will use. So here's the proof of the maximum principle. Let me take you back to where the maximum principle is. So what the maximum principle says, just as a reminder, is that if I have Laplace's equation satisfied or it's greater than 0, that the Laplace equation is bigger than 0, then if there's any time point inside D where U attains its max value, call it M, then U is identically equal to M. So so assume on the contrary that U is not constant. Really, I'm trying to show U is constant. Then you assume that it attains its maximum value somewhere at some point, which since it's C2 on a bounded domain, it has to by compactness, so it has to do that. So we know that it attains its max point somewhere, and call that point x0, y0, where that happens. Then by the mean value theorem, we have that this inequality that M is equal to U of x0, y0, and it's also less than or equal to M. So that integral is equal to M, because I squished that integral in between M over the boundary. But that's only possible if U is identically equal to M on any ball centered at x0, y0. That's because I didn't choose the size of this ball, right? This AB was arbitrary. And because my integral is equal to M for any choice of ball, as long as it's centered at x0, y0, that means that U itself must be M on every single one of those balls, but it's centered right at x0, y0. It doesn't mean that U is identically equal to M everywhere, just as long as I'm in any ball that's going outside of x0, y0. Now assume that there is some value, since I'm assuming that it's not constant, then there's some value out there far away from x0, y0, where it's not M. Since M's the maximum, I know it has to be smaller than M. Agree? And it's strict. So there's a picture of what's going on. So by continuity, I know that I can put a little ball around x1, y1, where U is strictly smaller than M inside that ball entirely. Remember that on each one of these circles around x0, y0, it's M. U is identically equal to M there. Well, I can make a path from x0, y0 to x1, y1. And I can do that because we always assume that omega is connected. My D's became omegas, didn't they? So along that path, so I'm starting from x0, y0. On that path, as long as I'm in one of those balls, it's M. Outside of that path, eventually, there's a point here where it stopped being M. It has to be, right? Because I've entered the realm of x1, y1. So in that world, all the U's are smaller than M. So there's going to be a last point, call it x2, y2, where it stopped being M. That was my last M. Right after that, it's M no longer. So there's my x2, y2 on the picture to give you a diagram. Draw a circle around that x2, y2. Well, by the mean value theorem, I could just do the same argument I ran for x0, y0, and there's a circle around, or there's concentric circles around, where it's identically equal to m on all those circles. But I can't do that, because x2, y2 was the last point. And right over here, to the right of x2, y2, it should be now smaller than m, and it's not. This implies that u is identically m everywhere. I can come up with uniqueness of solutions for Laplace's equation now from